in our previous week's material, we were focused on what does an evolutionary tree represent, right? Population splitting and changing through time, and a little bit of like how that's represented with characteristics being able to be put on the tree, like we did with the clade race and things like that. What we want to do now, though, is those were all kind of were coming from this assumption that we knew what the correct tree was. This next lesson 7 is really focused on what is the evidence that we use to favor one tree versus another. So to initially start with, the first section here is just why do we put traits on a tree in a particular way? And hopefully, as you were doing this, you had like you would say, okay, character 1, right? Everybody has it but the orang, so it must have evolved here and then been passed on to all the descendants, and the orangs didn't get it, right? And so that would make sense. Whereas like trait 4 would have evolved here and been passed on to humans, bonobos, and chimps because they all have it, but not before where gorillas would have inherited. So that's kind of the idea of like why do we put the traits in the particular part of the tree that we put them there? Sometimes we can't put them on in one spot and have it be inherited by their common ancestors. So for example, like character 2 here, humans and orangs both have it, but nobody else does. Well, we could that on there in a number of ways, but probably the most simple is to put it on here on the way to humans and here on the way to orangs. It must have evolved twice, an example of convergent evolution. Another way that we could try and do is we could put it on here, and then it's being passed on to everybody, but then have gorillas lose it, and then have chimps and bonobos lose it. A loss counts as much as a gain does, right? So if we put it here and here as a gain for humans and orangs, that would require 2 evolutionary events. If we put it here, there's 1, and then we have a loss on the way to gorilla and a loss on the way to chimp and bonobo. That's going to require 3 evolutionary events. We have to put 3 different tick marks on there. If we look, we can see how like this tree down here assumes that all traits were the result of convergent evolution, right? They all evolved independently in every lineage rather than being homology, rather than being passed on from a common ancestor. When we do it, if we focus on maximizing homology to have as many traits as possible inherited from a common ancestor, we get a much lower score. It requires a lot fewer evolutionary changes, right? So for example, with trait 1, if it were to evolve here, that would require 1 evolutionary change, whereas here it would require 1, 2, 3, 4 different evolutionary changes. And so that's why we prefer that, right? It's more parsimonious. It's a more simple evolutionary history. And so that's why we favor that one over the others. So that's just kind of getting us at that idea of why do we put them on the tree the way we put them on there? Because we're trying to maximize and have as much homology as possible. Now we're given 3 trees. Well, 2 trees and a non-tree, really. And we're asked to figure out, well, which one would have the lowest score? Which one would have the fewest number of evolutionary events required? And the one that has the lowest score, that's the one that is the most likely to have occurred. And essentially, if we look at this, it has 2 main differences, right? This one has crocodile and hummingbird as sister to one another, and then being those 2 sister to gecko. This one has crocodile and gecko as sister to each other, and then those 2 as sister to salamander. So a bit different, right? That they're inferring a different evolutionary history, primarily in these areas. This one also has salamander as the outgroup here, right? As more distantly related to everything else, whereas salamander is right in the middle here. So how do we know which evolutionary path was the one that occurred? Well, all we have to look at are the modern characteristics, and then take those characters and try and maximize try and minimize the number of evolutionary events to have as much homology there as possible. So as you go through a character one, right, everybody has it. So we're going to put that here, here on both of those trees. It doesn't help us distinguish between those two. If it's a non-tree down here, we'd have to have trait one evolve independently 5 times. Okay, so as you go through and do this, and keep in mind you can have gains and losses, right? That's something that we want to think about that can help cut down. We can have a character appear and then be lost, and that would require 2 evolutionary changes that may be better than having it gain 3 different times. So something to keep in mind there. But as you go through and do this, I believe the lowest score you can get is like 11 or 12 on this tree here, and this one it's somewhere around 15 is typically what I see students get. And then this tree is much, much higher. And it's much, much higher because everything has to evolve independently. This is why scientists accept the concept of common ancestry, that it just is a lot more likely event that trait one evolved once rather than 5 separate times to be the exact same, all these different species. Way, way simpler explanation to say there was a common ancestor that had that trait, passed it on to all its descendants. So based on that, though, I believe the tree one is our lowest scoring tree. That's the one that is the one we accept because it has that. This is essentially what scientists are doing when they analyze the characteristics in DNA of organisms. And they're trying and infer how, say, the evolution of insect wings occurred, how the evolution of different species occurred, how closely related are certain groups, what role did maybe some geographic events took place, what role did they play? All these things we can start to learn about when we can essentially come up with the path that evolution took, and can answer some interesting questions that way. Even when we start to look at some criminal trials have used this. So for example, there was I believe it was a dentist who had HIV, and they were able to basically confirm a cluster of patients. If you imagine the virus in a set of patients, right? That they all were grouped with this dentist, and that the way the grouping played out, right? That they had to get it from somebody in that group, and the dentist is the only one that knew he had it before he operated and worked on these people. There's some nurses that at one time in, I think, Liberia were actually imprisoned for spreading the Ebola virus when they were going in to try and help a population that needed some nursing. And when they went back and analyzed it, it actually showed that the Ebola virus didn't come from the nurses who were helping in another location, and they didn't bring the Ebola with them. The Ebola was there. And so you can kind of track some of that thing. You can essentially, Ancestry is using a lot of the same Ancestry in 23andMe. They're using the same concepts to help you identify relatives and things like that. And so it has some practical applications beyond just like learning about the world around us and how things occurred. But there's more complications to it. There's more technical details, but essentially that's what scientists are doing. They're scoring trees in a variety of ways, and then they can infer things based on that tree that we think is the most accurate. Let's see what else I want to mention on that. They obviously don't score it by hand the way that I had you do here, right? They're going to use a computer program to do that. And I think I showed you that in this video down here. And that kind of gets us to the last part of this lesson, right? Well, sometimes you'll hear people say, oh, well, it just appears to be common ancestry because whatever character one was so important that whoever intelligently designed these organisms must have needed that character to be there. And that's why we kind of looked at this idea of the DNA, right? If we can find something that does the same thing in all of these organisms, there'd be no reason for differences to accumulate that reflect common ancestry. So we have these physical characteristics that gave us this tree that tries to tell us, crocodile and hummingbird are more closely related than either is to a gecko. That seems a little bit shocking when you think about the physical appearance of some of those. But if we look at a character that should be the same in everybody, and we analyze the A's, G's, T's, and C's of that DNA, and we look for we run this same type of analysis, except for with DNA, having the computer score it. When we run that analysis, we see it tells us the same story, that crocodile and hummingbird are sister to one another. And if the gene is doing the same thing and the mitochondria is the same in all these species, why would it tell us the same story as these characters unless the evolutionary history, the mutations that happened to that DNA were inherited from a common ancestor, even when that DNA is not impacting the function of the gene in the mitochondria. And so that's a really strong evidence that common ancestry is supported by both the physical characteristics and the DNA, and link those two together.